Dear students, welcome to lecture number 8. And in lecture number 7, we have discussed details information regarding limit state methodology and how we consider various type of sections, whether it is balance section, under reinforced section, over reinforced section. And we have also discussed their merits and demerits and what is the codal recommendation regarding the design and analysis of a RCC section. So that comes under the flexural analysis and design of RCC beam. So today lecture is also important because we will be going to discuss some basic concept which will be helpful and guide us later on whenever we do any numerical problem on analysis as well as design of RCC structures. So today's topic, let us go through, and the topic basically we have to find out the methodology and the formulas, how to calculate, how to find out moment of resistance of a rectangular RCC section. So that means if you have any type of beam section which may be simply supported, it may be cantilever, any type of. So accordingly, whenever you have presumed some section parameters, sectional dimensions, as well as you have decided that what will be the grade of concrete, what will be reinforcement. So accordingly, when that beam will be subjected to loading and how that particular beam will be behaving, that means what will be its capacity to resist various type of loads and their movements. That means when what will be the movements, basically they are coming from the external loads, so their effects and how the particular section as per the decided configuration, decided parameters and decided material, how it will be able to resist the movements which are coming on it. So that means indirectly we can say what is the basically capacity of that particular beam or that particular section to resist the bending movements which it is going to be encounter. So that topic is movement of a resistance of a rectangular section. So let us try to understand. So title of this topic is analysis of singly reinforced concrete beams. So that means you will be able to understand that what is the meaning of singly reinforced. So that means as per the information which we have already discussed, we have gone through that there may be an example of a RCC rectangular beam, rectangular section, and we have provided reinforcement only in the tension zone. So that is termed as a singly reinforced concrete beam. So now we are going to discuss the analysis, how to do the analysis. Now you have to refer clause number 38 of IS 456, where information related to the analysis part is compiled. So in accordance with the assumptions which we have taken in the previous lectures, based on the clause 38 of IS 456, the analysis of a rectangular singly reinforced cement concrete beam, we can do it, and the information is explained hereafter. Now let us consider a rectangular section of a beam which may be subjected to loads, and ultimately that load will be subjecting such that it will be going to reach the ultimate limit state of stresses and strain. So that means in a rectangular RCC beam, concrete will be going to reach its ultimate stress as well as strain as well as reinforcement. So here you have to go through this diagram very carefully. So first of all, let us discuss about the section part. So this is an example of a rectangular section of a beam having some reinforcement at the bottom where tensile forces will be acting, and V is the width of the section, and similarly D is the effective depth of the section, and dotted line is indicating the location of the neutral axis. So as we discussed, we will give you the width of the section. D will be effective depth of section. Effective depth means it is the distance between topmost compression fiber of the section up to the centroid of the reinforcement which we have provided. Now we have to discuss there is depth of neutral axis. So you are aware that this dotted line is indicating the neutral axis, location of the neutral axis, and we are very much aware that when we are drawing any strain diagram for RCC section, then above the neutral axis you can see there are compressive strains will develop, and below the neutral axis we are expecting tensile strains will develop, and that will be considered when the ultimate limit state of stresses are reaching. So XU will be depth of the neutral axis, and then distance D minus XU, that means distance from neutral axis to the centroid of the reinforcement, that will be D minus XU, distance of neutral axis from center to center of the steel. Now this is the strain diagram particularly. You can see here the topmost fiber of concrete has reached its ultimate limit of strain as recommended by IS 456, and you can see here epsilon st is the strain in the steel at that particular level. So dotted line, again I am stating that it is a neutral axis. Now when we draw the stress diagram as per the theory which we have already discussed, you can easily see here above neutral axis compressive stresses can be seen. So this is a stress block for concrete, and as per assumption which we have taken, below the neutral axis we are not showing any compressive stresses. So we are ignoring the compressive stresses taken by concrete, and only tensile stresses are taken care by steel. So at the topmost level of, or you can say outermost fiber, you can see here this is compressive stress, maximum compressive stress, that is 0.447 FCK. So this information we have already discussed in the previous lectures, and the variation or stress distribution in the compression zone will be just like this figure which we have shown here. Some portion will be a straight line, and after that it will be a curved shape just like a parabola type, and the maximum stress at ultimate limit at the level of steel, that is 0.87 Fy. So we are just considering that at the ultimate limit state maximum compressive stresses in concrete is 0.447 FCK, and maximum tensile stresses are expected to be 0.87 Fy after the application of all the partial safety factors which are recommended in case of a limit state methodology. Now when you take out the area of this stress block, so we are considering that the total area of this stress block will be giving us the value of compressive force which is given as Cu. So Cu is the compressive force or you can say ultimate at the stage of ultimate limit state. So when ultimate limit state is reached, Cu will be giving you the value of a compressive force in concrete, and this will be the center of gravity of the stress block where the whole force will be acting. And as per the mathematics, which is not in your scope, you have to remember this formula, and the every information is given in IS code. So what we are considering that center of gravity of this stress block from the outermost fiber of concrete, it is given by formula 0.416 XU, where this is the depth of the neutral axis. Again, XU is the depth of the neutral axis. So 0.416 XU will be the location of the center of gravity of this compression block or compressive stresses block. And similarly, TU. Now TU is the tensile force in the steel at the state of ultimate limit. That's why we have taken in the abbreviation here TU, and T is for the tension and U is for the ultimate state. So that means you are able to here find out Cu is the compressive force in the concrete at ultimate limit state, and Tu is the tensile force in the steel. Now the distance between the line of action of Cu and Tu, that is known as Z, which is lever arm, because Cu and Tu, that means compressive force and tensile force in the section, they are forming a couple, and the lever arm given by this total distance was D, so D minus 0.416 XU. So Z we can calculate by this particular formula. So Z is lever arm between Cu and Tu, which are forming a couple. Now when we have to calculate the value of Cu, what is Cu? Cu is the total compressive force in concrete. So this formula is given by IS code. So you need not to do any calculation. You have to refer this formula, that is 0.36 FCK. B is the width of the section, and XU is the depth of the neutral axis. Similarly, TU is the tensile force in steel, which is given by tensile stress in steel and the area of tension steel which you have provided. So you have to calculate how much is the area of steel here, that is given by formula or symbol, that is AST. So area of steel, when you multiply area of steel by ultimate tensile stress in steel, so you will get this value, this formula 0.87 FYAST. So from these two equations, we can calculate the total compressive force in concrete as well as total tensile force in steel. Now in continuation to this, up to this we have gone through that how to calculate the compressive force in concrete and how to calculate the tensile force at the level of steel where reinforcement is provided. Now for the equilibrium of section, we will be considering that summation of the forces in the direction of compressive force or tensile force, that will be equal to 0. Accordingly, we can say Cu will be equal to Tu. That means at the ultimate state, total compressive force in concrete will be equal to total tensile force in steel, so that your beam section should remain in equilibrium. So that's why from the earlier these two formulas we can equate these two values, 0.36 FCK B XU, that is equal to 0.87 Fy into AST. And when you solve this particular equation, you get some formula, and that formula is, you can work out the value of XU. So what is XU? XU is the depth of the neutral axis. So this formula we are able to use, and if we have all the information, that means if we know the grade of steel, so ultimately you can get the value of Fy from the grade of steel. And if you know the area of steel, that means how many number of bars are provided and what is the size of one bar, that means what is the diameter of one bar. So from that diameter we can able to calculate the area of one bar, and the number of bars which are provided, multiplying it, we will get area of steel here. And FCK you can get the value from, this is the characteristics compressive strength of concrete. So that means if you are having the information that what is the grade of concrete which we have taken in casting this particular beam section, so FCK we can get from here, and B is the width of the section which is under consideration. So from all these values we can find out the depth of neutral axis. Also from this strain diagram, by taking the similar triangle equation, we can get also XU by D ratio, that is equal to 0.33. Here you can see, if you take this whole triangle, then this will be 0.0035 plus epsilon st. So that's why we have taken here 0.0035 plus epsilon st, and in another triangle you will get the value, that is 0.0035. So by taking the help of similar triangle theory, you can get the value of XU by D. So this will give you the ratio of depth of neutral axis to the effective depth of the section. Now this is the information which is based on the section which are given for the purpose of analysis. Now another very important aspect is you have to check what is the limiting value of XU by D, XU max by D, and that information XU max by D, limiting value of this for different grade of steel, is given in IS 456, and that is based on grade of steel as well as what is the depth of the section. So accordingly, if the grade of steel is Fe 250, that is mild steel, then the maximum limit, or you can say limiting value of XU max by D should be 0.5313. And accordingly, as you go for the higher grade of steel, then XU max by D value is decreasing. Now what is basically limiting value? Why we are taking the limiting value? So here you can note down this information. Limiting value of XU, that is the maximum value of the depth of the neutral axis which is restricted by IS 456, it corresponding towards the balance section at the ultimate limit state of a failure in flexure. So there are three cases. If the value which you have worked out by doing the numerical analysis, that means by doing the calculation, whatever the section which you are going to analyze, first of all you will be finding out the depth of the neutral axis. Then from the code we will be taking the value based on the grade of steel. If your value XU is less than XU max, then we will say that section will be under reinforce. And if XU is greater than XU max, then the section will be over reinforced. And third case, when XU is equal to XU max, then the section will be balanced section. So code is recommending you, either you can go for this value or you can go for third value. This value code is not accepting, so that's why XU can be less than XU max or equal to XU max. So this is the condition which is code is recommending. So that's why we are saying that depth of neutral axis which we are calculating by this particular formula, this is valid only when XU is less than or equal to XU max. So this information you have to take care, and then that's why we are taking the value of XU max, that is limiting value of depth of the neutral axis which is restricted by IS 456. Now another important point is which you are going to discuss today, that is moment of resistance of a rectangular section. As earlier I have told, it will be indicating the capacity of the section, rectangular section, based on sectional dimensions, based on the material, that means concrete, grade of steel, and how much reinforcement area you have provided. Now we can go through this diagram, which is the only stress diagram I have taken. So from this stress diagram, we can calculate Cg and Tg, which we have already discussed by a different formula. Now we can understand here that Cg is a compressive force and Tg is a tensile force. So that's why we have taken arrow in different direction. And now if Cg is equal to Tg for the balance, for the equilibrium of the section, then they will be forming just as a couple, and we can say that they are applying, or section has some movement of a resistance. So this movement of resistance will be against the bending moment. Now if the bending moment due to the loads is more than movement of resistance of section, then we can say that this particular section which is under consideration will not be able to resist the loads which are acting on the beam. And if the moment of a resistance is greater than bending moment, and then we can say that our section is safe in resisting the moment. And this information we will talk later on in details. So what we are here want to understand that Cg and Tg form a couple and create a moment of a resistance of the section. So ultimate moment of a resistance of the section you can get by this formula, that means force multiplied by, that means couple, because Cu and Tg are equal, which we have discussed. Either you can take the value of Cu or you can take the value of Tg and multiply it with lever arm value. So you will be able to get the ultimate moment of a resistance of a section whose dimensions, material, etc. you know. Now we have to check what code is saying, or code is recommending, or code is restricting about it. So therefore we can say ultimate moment of resistance, when you put the value of Cu, that means it is based on the concrete section. So it will be giving you this value, and this formula we can take from the IS code also. And this formula for ultimate moment of resistance is applicable for all value of Xu, or you can calculate it with the help of the steel. So in steel, this is the formula for calculating the ultimate moment of resistance, where Fy you know that it is the yield strength of the steel, AST is area of steel, Xu is the depth of the neutral axis. But you have to make sure that this formula is applicable only when either section is balanced section or section is under reinforced, because we are well aware now that code is never recommending over reinforced section. And I appreciate you, all of you, that you have asked wonderful questions so that we are able to discuss your queries. So again, I suggest you as well as encourage you to ask multiple questions so that we can clarify your doubts. Now, let us discuss about the limiting moment of resistance. So, limiting moment of resistance is, this information is available in IS 456 in annexure G. Now, what code is suggesting us? So, this is annexure G, and that is moment of resistance for rectangular and T section. So, we are now uh, getting information regarding the rectangular section. So limiting moment of resistance as per IS code, and condition is when Xu is equal to Xu max. So that type of section you can refer annexure G and the clause G1.1, where the section without compression reinforcement. So need not to worry. This is this is singly reinforced section. So very first point is code is saying that if the value of xud which you are calculating is less than the limiting value, then you can calculate the ultimate moment of a resistance by this formula. And if the value of xu by d is equal to the limiting value, then this formula can be used to calculate the limiting moment of a resistance. And if your xu by d is greater than the limiting value, then your section need to be redesigned. So in lecture number 9, we will be going to discuss some numerical problems. Thank you.